Hello, welcome to NPTEL online certification course on Introduction to Application of AI to Robotics. Today we are going to see Jacobian and Singularity. So I am going to take you through how in case of manipulator, how angular velocities and translational velocities they propagate from one link to another link, and through those relation we will be coming to the relation for the Jacobian, and we will be defining or we will be looking at what happens to this Jacobian when we are trying to find out the joint angles. Okay. So, then the concept of singularity will come. So, we are going to see through all these concepts in this class. So, I expect that by end of this lecture you will be able to understand very clearly how the linear and angular velocity propagation takes place, and you will be coming up with the understanding on the Jacobian and singularities, which are very essential for the manipulator design. The content for this lecture is I will be introducing the topic to you, then we will be seeing notation for time varying position and orientation. After that we will be seeing the linear and rotational velocities of rigid bodies, velocity propagation from link to link, Jacobian, singularities and Jacobian in AI and robotic applications. Okay. So, velocities and static forces lead to a matrix called Jacobian. Okay. So, that we are going to see, and as all of you know, velocity is derivative of position with respect to time, and in case of manipulator, the manipulator is going to have both the linear velocity as well as the angular velocity. Okay. And you see here velocity vector is always associated with a point in space. This is a very important concept which we all of us should always keep it in mind. Okay. And these velocities are relative to some reference frames. Okay. It could be inertial frame or it could be another frame. Okay. And as you know, speed is the magnitude of velocity without the direction information, whereas the velocity contains both information of magnitude as well as direction. So, let us see the notation for time varying position and orientation. Okay. So, suppose you have a vector say q over here. So, you have a reference frame say x, y here. Okay. And this frame is A on one link, and another link of manipulator you have frame B, and this vector q is defined. Alright. So, suppose this vector q I am defining with respect to frame B. Now, if I am interested in finding out the velocity of this vector q with respect to frame B, then I can take the derivative of this. Okay. So, suppose we are interested in differentiating this vector say q which is there in frame B, and essentially we are interested in finding out the velocity of q with respect to frame B. Okay. So, what we have to do as actually we have to find out this vector at time t plus delta t and subtract from this vector and divide it by delta t and take a limit with delta t tending to 0. Okay. So, velocity of a position vector can be thought of as the linear velocity of the point in space represented by the position vector. Okay. So, that is the notation which we are going to follow. Now, if q is not changing with respect to frame B, then naturally velocity is going to be 0, even if there is other frame from which q is varying. Alright. So, but if it is not changing in frame B, its velocity is going to be 0 with respect to frame B. Okay. Now, a velocity vector may be described in terms of any other frame. Okay. And the frame of referencing is represented with a leading superscript. So, suppose I want to describe this with respect to frame A. Okay, so this is how we can represent it. So d of qb by dt, and this expressed in terms of frame A. Okay. In general, a velocity vector is associated with a point in space, okay, and but the numerical value describing the velocity of that point depends on two frames, okay. One is the frame in which that differentiation is done, and the other is the frame in which it is expressed. Okay. So, suppose if A and B are the same frame, then we drop the outer superscript, okay, and then we basically write it like that. Okay. So, it essentially means that this is differentiated in the frame B and it is expressed also in the frame B. So, that is what is meaning of that. Okay. And otherwise, other way we can say for this one, if we want to remove this one, okay, naturally that we can do with the multiplication of a rotation matrix, that is, this is VQB, we need to multiply a rotation matrix from frame B to frame A, and then we can write it like that. Rather than considering the general point velocity relative to an arbitrary frame, okay, we often consider the velocity of the origin of a frame relative to some universal frame. Okay. So, if we have a universal frame, then to simplify our expressions, okay, we do not want to see that our equations are looking crowded. Okay. So, suppose if I am expressing it with respect to frame U, universal frame, then I just write it by Vc. Okay, it is a velocity of frame C origin expressed in terms of frame U, then I can just write it like this. Okay. So, velocity of origin of frame C expressed in frame A, though differentiation in U is given by this way. Okay. So, this way we can write that. Hope this is clear. Now, let us look at the angular velocity vector. Okay. So, the linear velocity vector describes attribute of a point, whereas the angular velocity vector describes the attribute of a body. Okay. So, suppose here we have a frame A, okay, and we have another frame B. Now, frame B is rotating with respect to frame A, then I can express the angular velocity of frame B with respect to frame A by this angular velocity vector. Okay. So, this way we can represent it. Okay. So, we always attach a frame to a body. We can think of angular velocity as describing rotational motion of a frame. Alright. So, this is how we do that. Okay. Physically, what happens at any instant, the direction of omega b with respect to A represents what? The instantaneous axis of rotation of frame B relative to frame A. Okay. And the magnitude of omega BA represents the angular speed of the rotation. Okay. So, this indicates angular velocity vector of frame B relative to frame A expressed in terms of frame C. So, this is the notation which we are going to follow consistently in this course. So, in the shorthand notation, okay, I can just write this as omega c. If I know that this my omega c is expressed in terms of a universal frame U. Okay. So, omega c is the angular velocity of the frame C relative to some understood reference frame U, then we can write it in the short form like this. Okay. And so, this omega c A in that case what will happen? So, is the angular velocity of frame C expressed in terms of frame A, okay, though the angular velocity is with respect to frame U. Okay. So, that is its meaning. Alright. Okay. Now, let us see the linear and rotational velocities of rigid bodies. So, suppose I have got a frame A here attached to a body. I have got another frame B over here, alright, and on this frame I am defining a vector, say QB. Okay. B subscript essentially tells that it is there in the frame B. Okay. And the origin of frame B is located through vector P B origin with respect to A with respect to frame A. Okay. Now, here you see three things are possible. Okay. And what are those three things? Okay. The one is that the vector P B origin, this can be changing. This is one possibility of the motion here. So, this vector can be changing. The second thing is that this vector can be changing here in that frame. Okay. And third possibility is that the orientation of frame B is changing with respect to frame A. Okay. So, this is the possibility. Alright. So, we can look at these three things, okay, separately, and then we can combine it. Alright. So, let us go for the first one. Here, let us suppose that RBA is not changing with time. Okay. So, say this frame B is not rotating basically. So, it is oriented at some orientation with respect to frame A, but it is not changing with time. Alright. So, you have this vector QB over here which defines the position over here, okay, and the origin of B is defined by PB origin with respect to A here. Alright. So, in this case the velocity of Q, okay, expressed in terms of frame A, okay, and defined with respect to frame A, expressed in terms of frame A, will be basically what? It will be the velocity of this point, right, the B origin with respect to frame A. So, this is B origin with respect to frame A plus the velocity of QB and this R B to A. Okay. So, this is what it is going to be. Alright. So, this way we can get the case when what? This is changing with time, okay, but the orientation is not changing. Alright. So, the velocity of Q with respect to A will be velocity of B origin with respect to A, that is the velocity of this one, plus velocity of this one Q with respect to B. Okay. And then since we are going to add it up, naturally both the velocities are to be expressed in terms of same frame. Okay, that is the basic concept here. So, okay, so that is why we need a transformation matrix, okay, rotation matrix from B to A. Alright, next let us consider only rotational motion. I am not going to consider either the translatory motion of the origin, nor I am going to consider the motion of the vector Q. Alright, I am not going to consider. Okay. Here we have the two frames, frame A and frame B. I am going to consider only rotation of frame B with respect to frame A. Alright. So, in this case let us see what happens. Okay. So, this is your frame A, this is your frame B, and say because of this rotation, this B goes to some position, say B dash. Alright. So, what happens? This was our Q2 original, okay, and when this has gone to B dash, this went to say Qt plus delta t, alright, after some time. So, this is the change in this case. Now, to understand this thing further, we can draw this figure, okay. Now, in this figure you see this is omega BA, alright, and say this is Qt, and this is say located at an angle theta over here, and this actually represents the angular velocity of frame B with respect to frame A. Alright. So, in delta t time, at an interval of delta t time, this is going to be the rotation of that is omega BA into times delta t, and in that time this Qt is going to reach from here to say here. So, naturally this is going to be the change delta Q. Okay. And you see here this delta, this AB is going to be what? Since this angle is 90 degree, this AB is going to be this Q into sine theta, because this angle is theta. So, we get this radius as delta Q, absolute value of Q and sine theta, and this radius is turning by this much amount. Okay. So, this is going to give me the delta S, basically the basic concept of arc length of a circle is r into theta. So, r here is your q sin theta and theta is your omega ba delta t. Okay. So, here this delta q is qa sin theta and that is multiplied by omega ba delta t. So, I can get delta q by delta t as this one omega ba qa sin theta, and you can see that what is this? This is basically the vector cross product. Okay. So, velocity of q with respect to frame A is equal to omega ba cross q A. Okay. Now, in general q may also be changing with respect to time with say frame B. Okay. So, this relationship we got when q was not changing with time in the frame B. Now, if that is also changing with time in frame B, then naturally we can add that velocity into it. Okay. So, this velocity of q with respect to frame B expressed in terms of frame A. So, that I can do, and then this superscript I can remove by multiplying this QB by the rotation matrix B to A, and this is the same one, and here the Q was expressed in terms of frame A, but I know the Q description with respect to frame B. So, again I use a rotation matrix RB to A over here. So, this way I can simplify it. Alright. So, if we have simultaneous linear and rotational velocity, so now I am going to come to a very general case. Okay. So, the velocity of q with respect to frame A, okay, and expressed in terms of frame A is going to be velocity of B origin with respect to frame A expressed in terms of frame A plus velocity of q with respect to frame B and rotation matrix RB to A, okay, because we have to express in terms of frame A plus omega BA cross QB or B to A. So, this component is due to velocity of the frame B basically, and this component is due to translation in frame where this vector is staying, and this is due to the rotation of the frame. Okay. So, this way we can generalize this relationship through these frames. So, this is your QB basically, this is your frame B, this is your frame A, and here you have the PB origin, okay, with respect to frame A. So, this way I can express that. So, this is the general expression. Here I am assuming the motion of this one as well as the rotation of the B, and I am going to use this relationship in the velocity propagation relation which we are going to derive. So, now let us consider the motion of the links of a robot. So, suppose I have got a link over here and this is say a joint axis I, okay. So, I can attach a frame to this link. So, this frame is say xi cap, yi cap, zi cap, okay, and zi cap is along the joint axis that we can see over here. Now, here this VII basically represents the velocity of the ith link, okay, with respect to a universal frame expressed in terms of ith frame. Similarly, this omega I angular velocity of ith link, okay, with respect to some universal link and expressed in terms of ith frame. Okay. So, this is how we can do that. Alright. So, now let us see first how the angular velocity propagates from one link to another link. Okay. So, suppose this is my ith link. Okay. So, here I have attached zi yi xi cap, okay, and this link velocity is VII translational velocity, angular velocity omega II, and here is my another link I plus 1th link, okay, and at the beginning of that I plus 1th link I attach this frame xi plus 1 cap, yi plus 1 cap, zi plus 1 cap. Okay. So, this is how I do, and these are the say translational velocity of origin of this frame, and this is the angular velocity of this link. alright, and the origin of this ith plus 1 frame with respect to ith frame is given by this vector, alright. So, what is the angular velocity of a link I plus 1? Okay. So, that is naturally going to be equal to the angular velocity of the previous link plus what? The angular velocity of that joint, rotational velocity of joint I plus 1. Okay. So, I am expressing this everything in terms of ith frame. So, this is I here, this is the I plus 1 joint velocity. Okay. So, I have to carry out a transformation here, multiply it by rotation matrix to change the frame from I plus 1 to I. Okay. And this theta I plus 1 dot is multiplied with this unit vector, and which essentially indicates that this rotation is in the z direction, which is the convention which we are following through the ds notation. Okay. So, I can simplify this equation. Okay. If I want to express it in terms of I plus 1th frame, then I can multiply this transformation from I to rotation matrix from I to I plus 1th frame, both the sides, okay, and this turns out to be simply this one, alright. That is link of angular velocity of I plus 1th link, okay, expressed in terms of I plus 1th frame is equal to angular velocity of the previous link plus that joint velocity of the I plus 1th joint. Then we can see how the linear velocity propagates, okay. So, in order to see the linear velocity propagation, as I said, linear velocity is always associated with a point, okay. So, when I am talking about linear velocity of I plus 1th link, essentially I am talking about linear velocity of this point, origin of I plus 1th link. Okay. So, this linear velocity of this point is going to be what? Linear velocity of this point, that is Vii, alright, okay, that is of the ith link plus this omega cross r component. Okay. So, this link angular velocity is omega ii cross this vector pi plus 1 with respect to I. And again I can express this in terms of the same frame. This is expressed in terms of ith frame. So, I can express it in terms of same frame if I do a multiplication of say I to I plus 1. If I do that both the sides, so right hand side is here and left hand side I can just simply express it like this. Okay. So, I hope these concepts are clear to you. Okay. So, the previous discussion was if we have a revolute joint over here. Okay. So, we have a revolute joint between this link and this link. What if we have a prismatic joint? Okay. So, if we have a prismatic joint, then naturally the angular velocity of the ith link is going to be same as that of the I plus 1th link, right. So, this is going to be the same, alright. And in the translational velocity component, you are going to have this addition extra, okay, because along the z joint axis you are going to have the joint velocity. So, in the translational velocity component which we have seen previously, we are going to have this additional addition. Okay. Next, let us see the concept of Jacobian, a very important concept. Okay. So, question arises, what is this Jacobian? Alright. So, to understand this, I want to make things little simpler. So, you say that I am talking about a tooling, say planar manipulator, okay. Say like this, I am talking about a tooling planar manipulator, alright. Say this angle is theta 1 and this angle is theta 2. So, its tip position is going to be function of what? X is going to be function of theta 1 and theta 2. Likewise, y is going to be some function, say g of theta 1, theta 2. Okay. Suppose we have to find out the velocity in x and y direction, then how can we do that? So, x dot will be del x by del t. So, this will be del f by del t. I have to take partial derivative because it is a function of both theta 1 and theta 2. Okay. So, this is del f by del theta 1 by del t plus del f by del theta 2, del theta 2 by del t. Similarly, I can do it for y. Okay. So, then on a matrix form I can write this over here, okay, and this whole thing I can write it in this form, okay, this way, into this theta 1 and theta 2 dot. So, this part is what we call as the Jacobian. Okay. So, Jacobian essentially maps these joint velocities, okay, that is the velocities in the joint space to the velocities in the Cartesian space. Okay. So, in robotics we speak of Jacobian, which relates joint velocities to Cartesian velocities of the tip of the robot arm. So, I can write it like this. So, this is a joint velocity vector, this is a Cartesian velocity vector expressed in terms of say 0th frame, and this is your Jacobian, which is function of theta. Okay. So, this Jacobian is a multi-dimensional form of derivative basically. At any instance Jacobian is a linear transformation, and this Jacobian will vary as function of time. Naturally your theta 1 and theta 2 keeps on changing continuously. Okay. So, with time your Jacobian is also going to change, alright. And the number of rows which you have here, this corresponds to how many degrees of freedom in the Cartesian space you have, and the number of columns which you have here, because these columns are going to be multiplied by this row joint vector. So, essentially the number of columns indicate how many number of joints your manipulator has. Okay. And the most general form is a 6 by 6 matrix, and this need not be the square matrix. Okay. So, for a general case of 6 joint robot, the Jacobian is a 6 cross 6, and theta dot is going to be a 6 cross 1, and we expressed in terms of 0th frame is going to be a 6 cross 1. Okay. So, the 6 cross 1 Cartesian velocity vector is actually the 3 cross 1 the linear velocity vector, and 3 cross 1 is the rotational velocity vector, okay, and effector, all those stacked together basically. Okay. So, what if I want to change the Jacobian frame of reference? Okay. So, suppose my this velocity in the Cartesian space, okay, is given with respect to frame B, and that will be the joint velocity vector into Jacobian expressed in terms of frame B. Okay. Suppose I want to convert it in terms of frame A. Alright. So, the velocity, translational velocity and angular velocity expressed in terms of frame A, here I can write this in terms of frame B, and with each one I can have multiplication with the rotation matrix. Okay. So, basically what we get, then I can replace this with this value, okay, here. So, what I get actually, this is my joint vector and this is my Cartesian vector. Okay. So, my Jacobian here is going to be this term, okay, and that is written over here. So, this way I change the Jacobian frame of reference from B to frame A. So, that way we can do that. Okay. Next important concept is that of singularity. So, here I was saying, okay, what our Jacobian does, Jacobian basically relates, okay, the joint velocity vector, okay, with the Cartesian velocity vector. So, what happens if I am interested in calculating this joint velocity vector? Then naturally what I have to do? I have to take the inverse of this Jacobian, right, and that has to be multiplied with this Cartesian velocity vector. So, what happens if that Jacobian is not invertible? Okay. So, when I am getting this theta dot joint velocity vector as inverse of Jacobian into velocity, and if the inverse does not exist, then what happens? Okay. The singular, and that is what we call as singularity, if your Jacobian does not exist. Okay. So, in general singularity means that no instantaneous motion along one of the Cartesian coordinate is possible. Okay. And what does that means? That means that manipulator loses 1 more degrees of freedom there. Okay. So, we can use the Jacobian to predict where these singularities occur. If you do not check for singularities, we end up commanding our joints to move at very high velocities. Okay. And at actual singularity, we would require infinite motion from the joint. Alright. So, there are two types of common singularity. One is what we call as the workspace interior singularity, and one is that which occur at the edge of the workspace. Okay. So, workspace interior singularity means basically when the two joint line up. Okay. So, suppose you have a link like this, the one link, and okay, and you have the another link say like this, okay, another link like this. Okay. So, if more than that is two joint axes, say if they line up together, so then that Jacobian interior singularity occur. Okay. And the second is at the edge of the workspace. Okay. So, if you have a say two link manipulator, then the edge of the workspace you have the other singularity. Okay. And in this singularity, why do we call this as the singularity? Because here at the workspace you see at the edge this cannot move in this direction. Okay, it can move only in this direction. So, effectively it has lost its 1 degree of freedom. So, this degree of freedom is lost, and that is what we call as the second singularity, okay, which occurs at the edge of the workspace. So, your structures can be designed to be singularity free, and Jacobian in AI and robotic application, if you look at, this Jacobian appears in modern AI driven robotics in the form of learning, control and planning, and we are going to see all these aspects when I am going to cover the AI aspect of this course. Okay. Next, let us look at resolved motion rate control. It is an important concept given by Whitney in 1969, which is about real time joint velocity control from the desired Cartesian velocity. Okay. So, essentially in the algorithm what happens at each time step we compute theta and then integrate it. Okay. Alright, then we do the integration. It is a simple, efficient and widely used in the industrial robot teleoperation and AI manipulation. There are singularity issues, drift accumulates over long trajectories and require accurate kinematic model. Okay. So, these are the things, and we can use these concepts in the deep reinforcement learning policies, often implicitly learn this RMRC like behavior. Explicit Jacobian provide interpretability and the safety guarantees. Okay. So, here are the AI approaches used in the Jacobian. So, these are the traditional control things. Okay. So, where Jacobian computed analytically from DS parameter, RMRC, operational space control, impedance control, all these concepts can come. Exact but require precise kinematic model, Jacobian based singularity avoidance you can have. Okay. And null space control for redundancy resolution can be there. They are used with the industrial arms. In the learning based control, we have the Jacobian estimated online from the data, say your neural network. Okay. Model free reinforcement learning can have policy gradient through Jacobian like operation. Okay. Simulation to real transfer, we can have Jacobian as bridge for the domain adoption. There we are going to use, we can have the learned inverse kinematic model, okay, through our neural network replacing the pseudo inverse. Okay. So, that can be there. Then differentiable robotics backdrop through kinematics is possible, and meta learning for the fast adoption to the new robot morphologies. So, if I want to summarize, so we have seen the velocity propagation, how the velocity propagates, both the angular velocity and the translational velocity. Okay. Revolute joints aids angular velocity, okay, fine, and sweep linear velocity. Okay. So, that is done, whereas prismatic joint aids linear velocity, translational linear velocity, that is all. Jacobian basically maps from the joint space to the Cartesian space. Okay. And each Jacobian column represents the end effector motion due to a single joint moving at a unit rate. Okay. And singularity, basically that is where your determinant becomes 0, they limit the motion, and AI robotics leverages the Jacobian for RMRC Force control, again this concept, how the Jacobian plays a role when we are calculating the, say, considering the static forces acting on the manipulator, and when we are going to evaluate how much joint torque we need so that the manipulator can resist those static forces. All those things we are going to see in the next lecture, and I am also going to discuss is a solved example on this velocity propagation, Jacobian evaluation, as well as evaluating the joint torque required for taking care of the static forces. So, in all these concepts we are going to use the concept of Jacobian. So, that I am going to discuss in the next lecture, and these are the references which you can look at, and thank you very much.